Hello again, and welcome to the third lesson this week on differentiation. We're going to have a look at the first of our trig differentiation lessons, which is going to be differentiating sine and cosine. So we're going to, again, at the moment, we're going to use what we learned about e to the x and follow the patterns and apply them directly to sine and cosine. You will be differentiating sine and cosine from first principles to prove these results later in the course after we've learned about small angle approximations. At the moment, we're just going to take it as read that these results are true. You'll also find using the chain rule next week will help with your understanding of these as well. It is important to note that when we differentiate any trig functions, our angles are always in radians, always in radians. So when we're asked to evaluate things, when we're asked to find equations of tangents, normals, gradients, anything like that, we have to use radians. And that will become clear when we learn small angle approximations and we derive these from first principles. So in general, if y equals sine x, then dy by dx is cos x. You differentiate sine, you get cos x. And very similarly to the e to the power of x examples we did, if y equals sine of kx, then dy by dx is k times sine of kx, which should be cos. Let's just change that right now. We've got k cos kx. Okay. If y equals cos x, then dy by dx is minus sine x, which is annoying. So you do have to remember these the right way around. Sine differentiates to cos, but cos differentiates to minus sine. But we can also apply the rule with k's. If y equals cos kx, then dy by dx is minus k times sine kx. So this will be a very quick video. Let's have a look at some basic derivatives and then have a look at a slightly more difficult problem. So we've just got to find for these three questions dy by dx. So y equals sine 2x. So dy by dx, the first thing I'm going to remember is that sine differentiates to cos. So I end up with cos 2x. And because k is 2, I need to multiply by 2. So sine becomes cos, and we multiply by 2. In our second question, we're going to have a look at y equals cos 5x. And the first thing I'm going to write down is that I know that cos differentiates to minus sine. And I'm remembering then that k is 5. So I end up with minus 5 sine 5x. So you can see that the 5 goes here and stays here. Part C, we're just being asked to do a slightly more interesting function. So we've got 3 cos x. Well, cos x differentiates to minus sine x. So we end up with minus 3 sine x. Okay, the 3 stays. And then we've got 2 times sine 4x. Well, sine differentiates to cos. The k value is 4. We take the 2 and multiply. And we can tidy that up a little bit and say it's minus 3 sine x plus 8 cos 4x. So these are pretty standard ones, right? They're easy to do on site. And like I said, the in-depth understanding will come once we've done first principle trig functions. So for a more interesting question, a curve has this equation. Find the stationary points on the curve in the interval 0 to pi. So our y is half x minus cos 2x. First thing, whenever we talk about stationary points, is we know that we're differentiating this function. So if we differentiate half x, we just end up with a half. Nothing different there, just as we always did. If we differentiate cos 2x, we get minus sine 2x. Then if we're subtracting minus sine 2x, we're going to be adding this. So cos 2x differentiates to minus 2 sine 2x. And if we're subtracting a minus, then we're adding. So for a stationary point, dy by dx equals 0. I have to tell the examiner that we know this, so we'll just write it in. So that means that 1/2 plus 2 sine 2x equals 0. And we're solving this equation between x is 0 and x is pi. So we'll rearrange our equation and we'll get it just on its own like this. We're solving a linear function of x here for the trig equation, so we're going to alter our limits. So our limits are going to change to 2 times 0, which is 0, 2 times x, which is x, and 2 times pi, sorry, 2 times x, which is 2x, and 2 times pi, which is 2 pi. And then we check the calculators working in radians, and we work out our principal value. So our principal value comes out at minus 0.253 to 3 sig figs. And then we find our other values. Okay, so we'll do pi minus this. Sorry, calculator's been a bit slow to wake up, so we'll have sine minus a quarter to get the principal value. And then pi minus our answer gives us 3.39 radians. Now we should keep collecting solutions that are in between 0 and 2 pi. This one's not between 0 and 2 pi, but let's keep going so that we've got all of them within 0 and 2 pi. So we've got 3.39, which is between 0 and 2 pi. Remember, 2 pi is about 6.28. And so to find the next one, we'll go back to our minus 0.25, and we will add 2 pi radians to this, because the sine curve repeats every 2 pi radians. So we end up with 6.03 to 3 sig figs. Now, if we kept going, the next solution that we would get would be this 3.39 plus 2 pi, which is going to be outside of our limit of 2 pi, 6.28. Okay. So actually, it should be 2x. The 2x's that we're interested in, that are in our limits, are 3.39 and 6.03. And then we can divide by 2 to find our x values. So 3.39 over 2, we just end up with 1.69. I left it unrounded in my calculator. And then the 6.03 divided by 2, there we get 3.02. And those are our two values of x, which give us a stationary point on that curve. And that's it. Okay. We'll get lots of practice in this week at this, and we'll have lots more practice next week. We will be looking at some the chain rule, the product and quotient rule next week, but we will also come back to trigonometry and look in more depth, and we will differentiate tan, sec, cosec, and cot, which will be incredibly exciting. Okay, thank you.